Hello everyone and welcome to Live from the Lab. This is the show where we talk about different technologies that Bruker has developed in order to help scientists discover the world around us. Today's topic is texture analysis. Now, you might remember about a year ago, we also talked about texture. So what is texture? Well, it's not how something feels. It's actually all about the orientation of the little crystals that make up the materials in the world around us. So, in order to learn more about the fundamentals of texture, we've put together a video to start out the show.
A great example of texture is sandpaper. Not in that it feels rough, but rather if you look at the surface, it's made of millions of tiny particles that can be oriented in a wide variety of ways. They could be randomly oriented, lying flat on the paper but random in rotation, or perfectly in alignment. The performance of sandpaper is dependent on this. If the flat sides are parallel to the surface, very little sanding can be accomplished. The orientation of crystals is what's measured in a texture experiment. In order to measure the texture of a material, X-ray diffraction is used. X-ray diffraction is a technique sensitive to the atomic distances in a material. In a texture experiment, the instrument is locked onto a single atomic spacing. Then the sample is rotated and tilted with the intensity of the emitted signal proportional to the number of crystallites oriented in each direction. Tilts can be accomplished by tilting the sample to the side, called side-inclination, or by offsetting the incident and diffracted beam, called iso-inclination. In the case of the strongest orientation, we can imagine every particle being in perfect alignment. If we project the surface normal of the crystals to a hemisphere surrounding the paper, we would see sharp spots positioned on the surface. Looking down on this hemisphere shows a radial map with sharp spots. It may also be useful to look at the face diagonal of the cube-shaped crystals. In this case, we also see a spot pattern, but the spots are located at different locations. And as a final example, we could look at the body diagonal in a similar fashion. In all cases, we see a spot pattern emerge with very sharp orientation. If we now perform a similar analysis on another piece of sandpaper where all the crystals are pointing straight up but they are randomly rotated, we see a slightly different pattern emerge. We see concentric circles centered on the rotation axis of the crystals. One last example to look at is one where the crystals are completely randomly oriented. Instead of spots or circles, the entire map is covered in constant intensity. Each of these plots is a map of a specific atomic plane of the crystal in the sample. These are called pole figures. In some cases, the pole figures are all that is needed and the job is done. In other cases, a single orientation model which takes into account the three independent pole figures is needed. There are many ways to model the crystalline components of a texture, including modeling an actual physical texture or using a series of mathematical equations. The end result is a single sample model which explains the measured pole figures. This sample model is called the Orientation Distribution Function, or ODF. The ODF uses a special coordinate system used to describe the orientation of crystallites in 3D space, called Euler angles. Euler coordinates have three values: phi1, phi, and phi2. The ODF is often imaged as a box shape, with the length of sides depending on crystal symmetry. In the case of a cubic crystal, all sides are the same length of 90 degrees. The orientation of each crystallite in the sample is mapped into this box. In the case of a single crystal, a small spot is seen. The more perfect the crystal, the smaller the spot. The more defects in the crystal, the larger the spot. This is where the term spherical texture comes from. In the case of a fiber orientation, we said the direction is well known in two directions, but random in the third. This would correspond to a line or fiber passing through the box, like a wormhole through an apple. In the real world, orientation components are often a mixture between spherical and fiber, known as an elliptical component. The last case was isotropic, where again it corresponds to intensity everywhere. It is often hard to use these 3D models in reports and for quantification, so often this 3D box is sliced into sections, resulting in a series of squares. Each square has a side of phi1 and phi, with each cut representing a specific phi2. Texture is important in optimizing both mechanical and electrical properties of materials. A random texture tends to resist brittle failure, as it is difficult for cracks to transfer from one crystallite to the next. On the other hand, the properties of a material, whether electrical or mechanical, are optimal in one crystallographic direction, allowing components to be pushed to new limits. Understanding the orientation of a material and the effects of processing steps on that orientation is important to unlocking its full potential.
All right, welcome back to the studio. I am joined today by Jonathan.
John, good to be here with my favorite host.
Yeah, so one of my favorite guests.
Yeah, that's right.
So everybody's my favorite guest. No, you're great. So materials research, always my first love, so we can always talk about those things.
Yeah.
So today's topic, though, is we're going to talk a little bit about texture. Now, we did talk about this about a year ago, right?
Yeah.
Right. So during that time, what we did is we went into how you actually collect the measurements, the different setups for that, and then how you get pole figures, and we just dived a little bit in the analysis.
That's right.
Right.
Yep.
So, but today we're going to do a little bit deeper dive.
Yeah.
So now, when we talk about texture, though, like we said, it's not about how something feels. It's not that rough feeling or even like a texture that you would apply in, computer graphics. This is different, right?
That's right. So we're talking about the crystallite orientation distribution in a material.
Yeah. So I always think about it that most materials out there, they are like sand on a beach, right? So it's made up of all these tiny little crystals, and they're kind of smushed together.
That's right.
And each crystal has a direction it's pointing, and that matters, right? It turns out in industry that matters.
It for sure does, because if you go down to a single crystal, that single crystal exhibits different properties along different directions, along the different axes, right? So it's very important for people that are interested in polycrystalline materials and engineering to get an idea of what the crystallite orientation distribution is inside, to know how the material is going to behave in different directions. Is it going to be isotropic? Things like that. If you don't have any features in the ODF, then you have a perfectly isotropic material. Right?
Yeah, and it's not always that the more texture, the better. Sometimes, if you have too much texture, it can lead to premature failure, fracture, or even that you've aligned a property too much in one direction and now it doesn't have that property in the other.
Exactly.
So it's about the right texture, and that's what we're talking about with X-ray diffraction, is to measure the degree of that texture.
Exactly.
Right?
Yeah.
So now, in terms of, like I said, we did talk about this about a year ago, although we have had some changes in the last year in terms of equipment that can do this.
Yeah.
So we do have the bigger machines, the D8 Advances, the D8 Discovers, floor standing type instruments. We can actually do this on a little bit smaller scale now, right?
So one of the coolest things about our new benchtop platform is that we can perform in-depth texture experiments, and we can calculate ODFs from that data. So kind of the full-featured texture analysis on the benchtop platform.
So the accessibility of these measurements now has greatly increased. No longer do you need that very expensive floor standing unit. Now you can do this on that smaller instrument.
Exactly. Yeah, it's pretty amazing. And so today I have data on the same sample. It's an aluminum alloy, and I've collected data on the kind of big bench, the big floor standing instrument, right, top of the line, 2D detector, microfocus source. And then I've also collected data on the benchtop, and we'll see how it compares.
Okay. Yeah, and there is value in all solutions. The bigger ones, we can measure larger samples, measure smaller spots, flexibility, things like that. So there is always that warrant.
For sure.
And it depends on everybody's application. And that's one of those things that you should always do whenever you're looking into analytical methods. If you don't have access to it right now, is try it out. Send some sample. There's some labs out there that do these analyses. Figure out what they are using. Also, you can always send it into a lab like ours, where we can run a sample or two and show you how these instruments will perform.
Exactly. Yeah.
So now you've put together some examples, like you said, right?
I do, yeah. So on the floor standing unit, we've done kind of the side inclination measurement, and then on the benchtop, we're doing that in iso inclination. So you guys saw a video earlier that kind of went into how those measurement schemes work. With ISO, we're doing a universal stage on the benchtop platform, the D6, with the phi attachment. So in that case, we can offset the incident and diffracted beams, and we can apply index phi rotation to fill in the intensity distribution.
So I think that might be a really important topic for us to talk about a little bit here. So side inclination, ISO inclination, right? So this is also a topic if you look at residual stress.
Yes.
Or texture. So when we talk about side, that's kind of the clear method. Say your diffraction peak is at 60 degrees. Okay. So what would you do? You'd go 30 in, 30 out, right?
Yep.
And then how do you now get the tilt?
Now I would tilt the sample using a cradle stage outside of the plane of diffraction.
Okay. So you need to have an attachment that goes into the middle of the machine, and that allows you to tilt the sample to the side.
Right.
Side
Hence
tilt.
side inclination. Right?
Okay. So now if you don't have access to that, or if you have a sample that's just too heavy, or some other limitation, how can we create tilt?
So we can create tilt by moving the actual, if you, let's say you do have a big sample, like an engine block or something.
Okay.
You can tilt the arms to basically get you tilt instead of tilting the sample. On the D6, we're still tilting the sample, kind of like a rocking curve.
Yeah.
But yeah, on a regular floor standing instrument, if you don't have a cradle, you can do the ISO method via tilting the arms instead of the sample.
All right. So you'd have, again, 60 degrees, so we come 30 degrees in, 30 degrees out, just like the other one.
Exactly, yeah.
And if the sample is flat, we'd say the tilt is 0.
Yep.
But now I could take the, like imagine the table here, we just take the table, we keep this there, and we just tilt the table this way, 10 degrees, 20 degrees.
Yep.
Or, like in the D8, we actually would just tilt the tube in the detector.
Exactly.
Like
so 2 theta is fixed, and you're just varying the omega, the incident angle, basically.
yeah. And then you just have the limitation of, depending on the peak angle, I can only tilt it 30 degrees if it's 60.
Right, exactly.
So you might measure higher angle or more peaks, right?
Yeah.
So let's go ahead and take a look at some of this data that you've collected.
All right, so we'll start with the 2D analysis the data that I've collected on the microfocus system with the fancy Eiger. So I'm just going to go ahead and import that real quick. And this is an aluminum alloy that's gone through some deformation, forming procedures and things like that. So we are expecting to see texture on this sample. And so you can see we're greeted. It pulled in the data pretty quick. And you can kind of see we have a ton of data over different 2 theta ranges. So these are basically snapshots of the detector snapshots at different sample tilts and rotations.
Okay, so this detector, this is like a camera. It can take a picture. And now when I look at that picture, what am I seeing?
So what you're seeing here is in the left to right direction here. Actually, if we go from right to left, that's increasing 2 theta.
Okay.
And if we go up and down, this is what we call gamma, which is in and out of the diffraction, so sort of in and out of the instrument.
Okay, so 2 theta, that's a different atomic spacing. If we think about that unit cell, that makes up the sample. This is, say, the top and the bottom of the unit cell, or the inclinated plane, things like that, like we saw in the video. Each of those is a different 2 theta, or a different ring.
Exactly.
Okay. So now the ring, I'm noticing here that the ring, it's kind of brighter at the bottom.
Yeah.
And it's dimmer at the top.
So that's one of the nice things about the 2D detector is you take one snapshot and you can see that there is inherently going to be some texture because we see that intensity distribution is not constant. It's changing. So.
Yeah, and when I used to do thin film work, we would look at, say, superconductors. And one of the big things out there in superconductor world is these, they call them a type 2. YBCO, yttrium barium copper oxide. It's like one of the only atomic structures to ever make it onto like People magazine. Or Time magazine. It was Time magazine. It's the only one to actually display it on the front. Because it could revolutionize the world, right? It superconducts liquid nitrogen temperatures. And the thing about it, though, is that these type 2s, you need to have strong texture in it. It needs to be all pointing the same way to get that current. And if you don't, well, man, that's like having a resistor right in the middle of your wire. So what we would do is we would actually grow it on tapes of nickel. And that nickel tape has to have a really, really perfect texture in one way. Well, when you're making the tapes, you don't want to have to do a pull figure all the time. And actually what we did, we just used a 2D detector. It was just put it up there, snap a shot. You could see the little ring. If it was, certain width, bam, we're good to go. I think it was like less than 9 degrees or something. Then you're good to go. If it's more than that, not going to be good.
So for a lot of people, stuff like that is all you need, right? So I mean,
that could be it.
We could just this software we can go a lot deeper if we need to, but you don't necessarily have to.
And in that example, we would actually take a sample. Every once, maybe you do it once a day, just to get the full orientation. Okay. So sorry about my interruption there. Let's get back to
it's all good. It's all good.
So we got the picture here.
Yes, so we're back on the computer. I'm just going to make this a little bit bigger. And so what we're going to do now is we have to define where our reflections are.
Yes.
So now we're basically just going to tell the software, this is the frame that I'm interested in looking at. And you just select, I'm kind of looking at where the fattest region is, maybe get some background in there. And then we can go ahead and create new pole figure.
All right. And wow, that pops up pretty quick.
Pops up pretty quick. And
yeah, it's pretty amazing because everything going on in the background there, right?
Yeah, exactly. So I mean, it's looking at the intensity across all of the different sample tilts and rotations and putting that into a nice little stereographic projection for me based on the coverage that I have and selected in my measurement.
So now I do notice on the bottom of the screen, there was like kind of the line with the peaks in it.
Yeah.
So that's actually the integration?
That's the, so yeah, we have this convenient 1D integration that will help you also. You can do the integration or select the peak using the 1D as well. So if I just do that, for example, you see it pops up with another pole figure.
Ah, there we go.
So instead of selecting the, using the ring cursor or the wedge cursor, I can use the 1D cursor and get a pole figure that way. So it's just a different way to import and analyze the data.
And that's one of the benefits of doing 2D is that one data collection, multiple pole figures.
Right, exactly.
So how long?
Oh, well, yeah, if you're when you're talking about that, yeah, I mean, you could see that we have 2 reflections on that one snapshot.
Yeah.
So the coverage of the Eiger is great because we're getting 2 for 1, a 2 for 1 deal here.
Sure.
Yeah, so.
All right, so you've made some pole figures.
Made some pole figures.
Now do we need to make more pole figures?
Yeah, I'm gonna make 4 for the analysis.
Okay.
So you can see I got my 2 from this region here. We have another one. So I'll use the ring cursor for this and then just import them. You can see I'm just building some data sets here. And then that looks pretty good. So there you go. I have 4 pole figures. I'm going to now make this smaller. The analysis, the frame portion, so we can see these pole figures in a little bit more detail.
So now why, this is one sample. Why do they all look different?
Because we're looking at different directions along the crystal axis. So it's a combination of process and crystal symmetry that we're seeing here.
And that's why we don't necessarily have to take the full pole figure.
Right.
For each one, you can use them to reassemble everything that's going on.
Exactly, yeah.
It's almost like if this was a globe, you have satellites pointing in different directions.
Exactly, yeah. So, I mean, back in the day where you needed to have a lot of coverage, it's not really the case anymore. So the software, when we perform an analysis, we can use multiple pole figures to make up for that.
All right. So now the first step, though, I guess, is that we have to somehow label these. Yeah,
so we're going to go ahead and do some indexing now. The software will allow me to say that this is an FCC aluminum alloy, so I can just say aluminum, and it'll go ahead, and if I hit index, it'll go ahead and index. So it automatically indexes the 4 pole figures for me.
So what if my material is not present? Can I add it?
Absolutely. So there's a materials database here. I'll just open that up briefly. And what's nice about this is we have an entire set of common materials that people are going to do texture analysis on. You can also import crystal information files, structure files, and things like that, or you could build something from scratch. And there is quite a bit of information in here. So if we go to the aluminum, you can see I have full structures.
Oh, yeah, I can actually see it here now.
Yep, so you can see where the reflections are going to be in diffraction. And there's a ton of other properties in here as well.
And that can be very useful for planning the measurement, too.
Exactly.
Okay.
Yeah.
Okay.
So
now on the pictures, though, I see we have these numbers.
Yes, so we have the, you're talking about the reflections?
Yes.
Yeah. So those are the crystal reflections.
All right. So, and that's something called Miller indices.
That's
so
right.
If anybody wants to know about it, there's a lot of great content out there. I don't think we've done one yet on it, but like, for example, 111, that would mean it's the diagonal plane.
Yeah, exactly.
Right? Okay, and then 200, that's kind of like...
along the face, right?
That's along a face, but because it's a 2, that means it's half of the unit. So
exactly. Same direction. Yeah, exactly.
Yep. Yeah. Okay. So those basically designate what orientation we're looking at in the unit.
Yep. So from here, I mean, this might be enough for some people, right?
Yep.
If you just want to see, does my material have texture, you can kind of see what the symmetry is. Now, I will say I did a pretty poor job of mounting the sample to the process symmetry that I used, because you can kind of see how this symmetry lines up. But what I can do is I can go in and actually rotate the pole figures to bring it in line with the process symmetry that I've used.
Because that is an important fact here. I mean, you have to understand there's crystal symmetry, right? And that's the Miller indices. That's seeing that unit cell, what it looks like. But then there's process symmetry, right?
Right, exactly.
So, and process symmetry has to do with the processes you do. Are you rolling the material in a certain way? Are you punching the material? If you're depositing it, or is it coming in at a certain angle?
Exactly.
So be thoughtful when you mount it. How do you mount it?
So this sample was a circle, so it was kind of hard, and I didn't have the. You can label it to align it with the process symmetry. But typically, source to detector is the rolling direction. And with the default settings, you can change that though.
All right.
So yeah, it's kind of gives you the power to do what you want.
All right. So you can turn it. Here we look like you've lined it up pretty well.
Yeah. So did my best job there with the rotation of the pole figures. Now we can go ahead and do either a component or harmonic analysis. I think we'll start with harmonic.
What's the difference?
So component is more of a model-based relationship of so you're looking at sort of individual texture components that comprise the pole figures.
Okay.
In the case of the spherical harmonics, it's more of an analytical approach to determine the orientation distribution function.
Yeah, so it's measuring the pole figures using mathematical models, and then you extract the orientation of those math models, and that's how you would build it up.
Exactly.
Whereas, like you said, component method, it's a newer method.
Yeah, it's kind of like a refelt refinement almost.
Yeah, where you're actually doing real modeling. You're saying, I got this much of this, the grains are pointing this way, and so many of the crystallites pointing that way.
Exactly,
So very, very interesting approach to actually bring to the software, and I think unique actually to this.
For sure, and there's some new things in there with this software at least that I'd like to show with the component modeling specifically.
Okay, so spherical harmonics, great way to start, especially if you got good coverage here.
We'll go ahead and just perform a quick few of them. So you can see if I click the spherical harmonics after I've defined my sample model, it's going to ask you what kind of process symmetry you have. I'm just going to start with orthorhombic so you can see, and then I can choose the rank of the expansion. Higher the rank is going to give me, allow me to see sharper features.
Okay.
Or resolve sharper features. And then there's the positivity method, which basically just allows you to minimize the negative values in your ODF. Right. So, and that basically, theoretically shouldn't have any negative values, right? So I'll turn that on, and we'll just choose kind of a more conservative rank in the expansion here. We'll say 6 for now. And for the augmented rank, maybe 12, let's say. Let's start with that and see where we end up. And just hit OK. It's going to run the evaluation. And you can see I have my experimental pole figures, my recalculated pole figures, and my difference pole figures. So the idea is you want to minimize the difference pole figures, right?
Yes.
But you can kind of see, since I chose orthorhombic symmetry, it's forcing me into this fourfold symmetry in the pole figure, whereas I might not necessarily have that. So let's just do the same thing, but I'm just going to choose monoclinic instead. And we'll do, let's do, because I do see that my features here aren't as sharp as I want them to be. Let's increase the rank of the expansion. We'll do positivity again, and we'll do 16 for the augmented rank.
Yeah, so, I mean, two things to think about here. Number one, with that rank, you set it as too high. You can fit anything anyway. Right. Right? I mean, and I don't care what kind of fitting you're doing. If you're doing Reet felt, if you're doing this, you turn on enough stuff, it will give you a beautiful fit. That's
right, yeah, and the issue with overfitting can be just noisiness in the data too. Yeah. So you want to just kind of, I always start out a little bit more conservative and then work my way up.
Yep. And are you fitting the true reality?
Right, exactly.
Occam's razor, simplest approach the best. And then the one other thing, just to reinforce, there was that process symmetry there. There might be some people out there going, wait a minute, aluminum's cubic.
Yep.
What are you doing here?
Yeah, exactly.
Process symmetry is not the crystalline symmetry.
Right.
This has to do, like you said, when you look at that pole figure, do we kind of got fourfold symmetry going on? Do we got twofold symmetry?
So you could just see the difference right there.
Yeah, immediately.
So it's constraining, with orthorhombic, it's constraining it to fourfold, right?
Yes.
Whereas monoclinic, it's freeing that up a little bit more. So you see more asymmetry in the pole figure, in the recalculated.
Yeah. So now when you look at these, what's telling you this is good or I got to tweak it more?
What's telling me is, am I seeing all the features that I want to see? It's also, are my features too broad in the recalculated pole figure.
Okay.
Do I need to try to increase the rank of the expansion a little bit more? The difference pole figures also help you see, am I missing anything?
Yeah.
So this is actually not a super bad fit.
Okay.
So if we were to just increase the rank to, let's say, 14 and then 24 for augmented, you'll just see it'll tighten it up a little bit.
Yeah.
Yep. So now I'm able to fit sharper features. And one of the nice things is if we go to down here, we can see kind of what the complete pole figures look like. And one thing I always watch out for is on the edges here, if you're overfitting, you'll see these weird oscillations.
Yeah, you start to get like these little lines or divots, and
exactly.
Just be thoughtful. That's probably not a real thing.
Right.
And again, that old thing, simpler, better.
Yep.
Occam's razor. Fit it with. You're often better going with something that the fit doesn't look as good, but it's a much simpler.
And
fit.
again, you want it to be grounded in reality. So,
right.
Yeah.
Right.
100%.
So now from spherical harmonics, though, you can do, like you said, the full pole figure. So here we go. Now we got the full one.
Yep.
What else?
So
what other views can we get of the result?
So we can do the inverse pole figures as well. So you can see here in the rolling direction, and this is going to depend on how you rotate your pole figures too,
Okay.
and how you define your rolling direction. But in this case, rolling direction, we're seeing basically 111 and 001.
Okay.
In that direction. Transverse direction, we're seeing 110, and normal direction also 110. A little bit of 112 in there.
So when we're looking at this RD, TD, ND, RD means, so if it was the table here, RD would be, say, left to right.
Yes.
That's the direction of the process when they made the table.
Yep.
It's going that way. When we mount it in the goniometer, we put that left to right.
Yep.
TD, what direction is that?
TD is going to be transverse, so that's 90 degrees in the plane. So,
so
basically
towards
in
the
and out.
camera.
Yeah, in and out of the camera, exactly.
All right, and then ND.
ND is going to be normal, so
straight up.
Straight up, yeah.
Okay, so then this is saying, because we got the red spots in the RD, so pointing that way, it looks like we have a lot of 111s.
Yeah, that's right.
And a lot of 010s.
Yeah,
Or
001s. Yeah.
001s.
Yeah.
001s.
Yeah.
Okay.
And then transverse and normal, we got a lot of 110s. Or
So all the 110s are pointing that way.
Yep.
Or 101s are
Yep.
pointing that way or this way.
Yep.
And then you said something, though, about a 2, because I don't see a 2 on one of the corners. So how did you get a 2?
So if you add these guys together, this is basically where that stands, right?
Okay.
So this is the 112 if I were to just draw that here.
All right.
Yep.
All right. So just a different view of the way that this data is put together.
Yep.
This is used a lot by metallurgists, I know.
That's right.
Right?
Yep.
So, all right. So we got that. And then we got the, kind of the mother of all.
Yeah, that's right.
Which is the ODF.
So if we go to ODF view.
Whoa, look at that.
Yeah, I can try to make this a little bit easier by increasing the number of columns. But you can see we have texture components here as we go through our phi-1 slices. We have at least, what is that, 1, 2, maybe 3 at least components in here that look to be somewhat spherical in this case. So yeah,
and this represents, again, you take the slices, you stack them up, you build a cube. This is a cubic material, so you build a cube, and then you could look at that spot. How does the spot move through the cube?
Yep.
Right? And the sharper it is, then the sharper the texture.
Exactly.
So again, when we used to look at stuff like this, what we would do then is we would say, I know in this slice, I need to have a spot at this spot, this area. And if we saw that, we're good to go. And then we might say, and in this slice, that spot better be gone.
Right.
So these are the types of analysis that people sometimes do with this.
Exactly. And one of the good metrics here is texture index. If you want to see what the sharpness of the texture is, it's kind of like one way to look at it. And
so the higher that number, the stronger the texture.
Right. Exactly.
All right.
Yeah.
All right. All right.
So this was kind of just a dive into spherical harmonics version of the analysis. Now I'd like to get into and spend a little bit more time on the component model.
Okay.
So if I'm in the same data tree here, I can just click component method. It's going to ask me what pole figures I want to use. I want to use all of them because I collected the data. So, I mean, why not?
And for everybody out there, today you can see we're doing a deep dive, and that means we might go a little bit long. So if you got to go, that's all right. Go ahead, type any questions that you're thinking of right now on the side of the screen. If you're watching it later, you can always come back, watch this later, and you can send those questions in. Our email address is live.events@bruker.com. So send them there, and then we will get back to you with any answers that you have. So,
yeah.
All right, so now component method. So a little bit different.
A little bit different, yeah. So now we're doing kind of the more modeling approach and kind of refinement of the model approach to determining what the texture of the material is.
And to me, I guess from my materials background, I always thought like this makes sense.
Yeah.
Because I'm going to now build the sample virtually. We're going to throw in different components of texture, build it up.
Yeah.
All right. Sounds really complicated.
It sounds complicated, but it's not really. It's simpler than you think it is. Just because, you know, it's a matter of defining what the components are and then refining them to what your experimental data is. You know, same way that we do retail.
All right, so you made the pole figures, you index the pole figures, you just choose component method, and they're greeted now on the left. That's the column with the data. The middle is what's currently being fit, which there's no components.
Right, we haven't determined anything yet.
Isotropic, meaning it's everywhere.
Yep.
And then the right, that'll be the difference.
Exactly.
All right, so what do we do?
So what we're going to do is we're going to add some components to our model.
Okay.
You can see I have a number of different process symmetries here, even some that I didn't have access to with the harmonic method. And then we have our crystal phase, which we already determined. We have the component model, which we recently added elliptical components, which is really cool. I'm going to start out with spherical components here. I know I have biaxial texture. It's not a fiber. Could be somewhere in between, which is where the ellipse really helps out. But I'm going to start off with spherical components. One of the really cool things, if we go to orthorhombic process symmetry in spherical components, we have a bunch of predefined components that commonly metallurgists will use. And these are basically just going to have predefined phi1, phi2 locations, basically the location in the cube in the ODF.
All right.
And then you can basically decide, do you want to constrain that, let it float a little bit? So it's kind of like refelt in that sense, where you can play around with it. We're going to just start off by making our own components. So I'm going to do the same process symmetry I used in the harmonic method, so monoclinic. And then we'll do spherical components, and we will select the hotspot here. And
so I see you're pressing Control.
Yes, so I did Control on the keyboard, and then left-clicked on a intensity hotspot, basically. And you can kind of see, based on the crystal symmetry, if I were to rotate the axis here, I would hit, you know, based on the crystal symmetry, multiple positions. So, and you can kind of see where these dots come in here and show you what the process symmetry constraints are and the crystal symmetry constraints.
Okay.
So you can see this is actually pretty nice. Like I'm seeing spots where I would expect them if I have a certain component at that location. So we're going to add that component. Now you notice how I don't have any spots here.
Yeah.
So I'm going to add that component as well. And then we will go ahead and do a fit. So this is, if I switch tabs here, this is basically the components I have in my model.
Okay.
And what I can do is now refine that. So I'm going to start the optimization. We're going to let everything float. You can see here I can constrain the phi1, phi2. I can constrain the spread. I can even constrain the volume fraction of the component if I want to. But I'm just going to let it all fly today. And so we'll start the optimization. And we can see how the recalculated pole figure looks.
All right, there we go. So it's already looking pretty close. Now spherical means it's going to be like modeling it like we saw in the video, just kind of a little sphere, and it changes the size of the sphere. And okay.
That's right. So you can see kind of close. Maybe we're missing some of the broadening there if we were able to model it via some other method. But first, I think if we look at our difference pole figures, that'll help us in determining if we're missing anything. So what I'm going to do is I'll just click maybe like right here where that red spot is. We'll add that as another component and go ahead to the model and refine.
Yeah, because some of these features are kind of elongated.
Right.
And if we want to fit them with circles or spheres, then you kind of got to put multiple
spheres in place to make that,
to build it.
That volume element, right, exactly. So you can see that kind of got a little bit better. where I see a lot of elongation is right here, so maybe I'll add another one. So if I go ahead, add component, and hit play, we'll see this model get even better.
Mm-hmm. And then in the bottom of the right side, you can actually see the contribution just from that particular
exactly.
component. Right?
So you can see what the contribution is to the individual reflections. Okay. You can actually model what the component looks like relative to the lab frame, and you can look at what is the relative volume fractions of each of the component.
And as you're building it up, one little tip is if you see any of those components going to 0, just go ahead and delete them.
Probably doesn't exist if it's going to refine out. Yeah, exactly. So you can kind of see, it's capturing most of what I would expect from my experiment, but there's maybe some broadening that it's not accounting for. But now what I'd like to do is show the elliptical components.
Okay, so now the fit, the degree of how good your fit is, that's called a chi-square, and that's shown in the upper right there.
Yep, right here.
Chi-square, and so where are we at?
0.8-ish.
0.8,
yeah.
Okay. And we had to use how many components in order to obtain?
I have 4 components defined right now.
4, and then the isotropic, that's just kind of the random part.
Exactly.
Okay.
So if we go to, I can just make as many of these as I want. So I can just click component method again. So we could hold on to this one. Go back to our model. And I'm just going to add a monoclinic process symmetry of elliptical components. And now you can see we have a lot more math going on here, because now we have the orientation of that ellipse in different directions, spreading differently in different directions. And I'm looking at this right here. So this almost looks like an ellipse, right? Yeah. It was meant to be. So I'm thinking this will fit really well with an elliptical component. And the nice thing is, if I have the computing power, I could just add as many of these as I want. I'm just going to add the 1 for now. Oop, did I accidentally add 2? I might have. Get a little click happy.
You got a little ambitious there.
Yeah, that's right. So let's see. We'll let it finish, and then I can readjust.
And so right now, actually, I think it's just refining the 1 component, right? Because I'm guessing you pressed that.
Yeah.
But we'll want to refine it now with both of them refining.
Yep. Oh, no, so there is both in there.
Oh, okay.
Okay. All right, that actually looks pretty good. And you can see the phi 1, phi 2 values are slightly different, so they could be different components, actually. So, yeah, I mean, this definitely looks like I only have 2 components now, and I have a much better fit. Versus
the 4 that you had to use previously.
Using a spherical.
Yeah, and that actually plays out then in that chi-square value. It was 0.8 before, 0.58.
Yep, exactly. So I can refine that again if I want. I could add more components to refine that chi-squared value, even make it look even better. But at this point, I think this is pretty reasonable.
And if you were doing this in an industrial environment, you can save those components.
That's right, yeah.
And then bring them in, do the refinement on just that one.
So you can import and export components here.
Okay.
And then if you wanted to constrain them in your future fits, you can do that too.
All right. So now ultimately, I guess the question is, now that you've done this, how does the analysis compare between circle harmonics and this? Are we getting the same end result?
Well, if we go to our ODF, you can see components are kind of in similar locations compared to the harmonic. We go to I can add some recalculated pole figures, so we'll do just kind of the similar ones, 1, 1, 1. And then if I go back up to my spherical harmonic fit, which was right here, looks pretty much identical. Yep. You see a little bit more noise here in the harmonic fit relative to the component method. And then we get the inverse pole figures. Pretty much the same thing that we saw with the harmonic fit. So you see the rolling direction here, 1, 1, 1, 0, 0, 1, and then transverse 1, 0, 1, normal direction 1, 0, 1, and then 1, 1, 2.
Yeah. So it's really, it's between the two, with component method, it's a little bit more stabilized because we're going back to the fundamentals of this is built up of units rather than being built up of mathematical functions.
Exactly.
Okay.
Yeah. So the last thing that I wanted to show today was how does the D6 data compare?
Okay.
So we'll just kind of go through that using the component model and seeing how it compares with the D8 data. So if I create a new document, see we're really loading the software up now.
Yeah.
That's right.
It's a lot of data.
It is a lot of data. And then
it's
I'm
just a laptop.
Yeah, I know. It's crazy.
Yeah.
So I'm going to import the D6 data, and these are just 0D phi scans, rotation, different, I guess, incident angle.
Yeah. Yeah.
And then you can see this is a lot easier because I don't have to, like with the 2D frames, it's just more.
So with 2D, you have to make the pole figure.
Right.
You have to tell it this is where the peak is. With these, because they were 0D scans collected right out of the wizard, they just pop up.
Exactly.
Okay.
Yeah, so you can see I have the same issue with the position that I put the sample on the stage. So I'm going to have to rotate these pole figures. So we'll do that and try to bring it in line with the process symmetry. So there you go. Oh, I was way off. So there we go. That looks good to me. And then I can go ahead, index these kind of the same way that I did with the 2D data. You can see indexed automatically for pole figures. You can see these are higher order reflections because then I can get my source and detector close together and I don't go, I get more coverage effectively.
And a common thing might be, they look at this versus your other pole figure.
Yeah.
And somebody goes, you can't do it.
Yeah.
We don't have coverage of the pole figure. But that doesn't really matter if you take more than one pole figure, right?
Right, exactly. So you make up for that by taking multiple pole figures.
So again, if we go back to the analogy, satellites, if you try to have one satellite, takes the whole picture of the Earth. No, here what we're doing is we're just saying we're going to put different satellites, take different pictures, and then reconstruct the Earth.
Yep.
That's what we're doing here.
Exactly.
It's okay. It's okay that you don't have all of it. You can just take multiple.
Right.
Okay.
So one thing I want to do is I do want to add the absorption correction for ISO inclination. So that's a new feature in the software.
So that's because
they've added this.
different incoming angles
penetration depths.
gives you different penetration.
Exactly.
Okay.
So you can see right off the bat, if I look at the 400, and I go back and I look at the 200, you can see these elements are very similar.
Yes.
Because the direction is the same.
Yeah. Yeah.
So that's encouraging to see. We can go ahead and then do a component fit. And in the same way that we did, we'll use elliptical components as well, because I love elliptical components. It's my favorite thing now. We'll go to monoclinic ellipse, hit on the spots. I'll add that component, and then I'll add the one down here. Add both of those. I'll refine them together.
And as you're putting it in, one thing that's kind of neat is in all of those different pole views in the left column, you see the dots pop up.
Yep.
And those dots actually correspond to the same component.
Exactly.
And that's why it's that you're refining one component against all of the pole figures.
Right.
Yeah.
So that looks really good right off the bat.
Yeah. Yeah.
So my recalculated pole figures using these two elliptical components looks really solid. I'm pretty happy with that. So now if we go over to our ODF, you can see very similar. Just make this.
Yeah, sure enough. We got kind of that little dot on the left and the right.
Yeah, and you can see this little guy here. If I go to the inverse pole figures,
same information.
pretty much exactly the same.
Yep.
Yeah, same information. I can even generate now that I have the orientation distribution function, even though we didn't collect this data, I can go ahead and generate the 111 pole figure.
There you go.
And it's exactly the same as the one that we collected here.
And I think in a lot of ways, this is the smart approach. If you are going to, if you said, I need a full 111 pole figure, rather than trying to collect it, because you get into so many issues with the measurement. As you go lower and lower, even with side tilt, as you go lower and lower, you start shooting, you're going to have to shoot in the side of the sample.
You run into the beam issues and geometry problems.
Yeah. So even if you can, the more robust approach truly is to collect multiple pole figures, refine it against a single model, and then produce the total pole figure.
Yeah, I agree.
So yeah, even if your analysis is not ODFs, even if it's not inverse pole figures, if it is just saying, I want the pole figure, this is the smart way to get the whole pole figure.
Yeah.
All right.
I totally agree. And yeah, you can see that D6 does a really good job.
Yeah. Now if we compare that, so there's the D6 one.
Yep.
Now let's see, what did it look like on the same one, the component one?
Same pole figure?
Yeah, the component one on
So this is actually the D8, because you couldn't tell the difference. Exactly.
Okay, so that's the D8 one.
And this is the D6.
It barely moved.
Yeah, it's probably because I had error when I rotated the pole figures, so that was my...
You were the problem.
Yeah, exactly.
And even the number, so in the bottom, for everybody out there, the min and the max, that's an idea of the scale. So when we think about the green, to the red, that's kind of your boundaries for min and max. And so that gives you a rough idea about how strong the texture is. And the fact those numbers are the same.
I know, it's pretty amazing.
That's right on point.
Having consistent data across 2 platforms, it's always encouraging to see.
That's right. All right, so we are at the point now. What we're going to do is answer some of your questions. If you have any questions, go ahead. Put them right now in YouTube on the side. Otherwise, if you're watching later, you think about something, live.events@bruker.com. Sometimes we can't get to all of your questions because you have a lot of questions. So go ahead, send them there if we don't get to it. So to start out, we actually have a question that came in before the broadcast. And by the way, for any future episodes, if you do have questions, you can always send them into that address too, and we will answer them here live. Why do you need a bigger instrument if the D6 does texture? So we did talk about this a little bit, but yeah, why? You just showed me.
I know.
Same data. Why would I ever want or need the bigger machine?
It is incredible what the D6 can do. The D8 can do a lot more in terms of being flexible. How I set up the experiment. You have the nice 2D detector. I can, for in the case of microdiffraction, that's not something I can do with a D6.
Yeah.
So there are more experimental limitations with the D6, but if you have nice flat samples, the D6 will do a nice job for you.
Yeah. If you want to measure something like the texture on a little spring that comes out of a pen.
Yeah, right.
A tiny little spring, you're going to need a tiny spot. It's going to have to stay in the center, right?
Yeah.
If you for some reason need to do side inclination, you got to have it.
Yep.
So like we said, small samples, but also big ones, right?
Yeah, exactly. I mean, if you want to be able to put something that's multiple kilograms on a stage, the D6 is not going to be the answer for you.
Yeah, the D8 will be able to do it, and it can also do it in ISO.
Yep, that's right.
If you don't want to tilt to the side. So there's the right tool for the right job.
Yep.
D6 can do a lot of jobs.
Yeah.
Sometimes the D8's needed for those jobs.
Exactly.
And you also don't have to go all the way to a Discover. You can do this in an Advanced too.
For sure, yeah.
So, all right, so next question, and we have a lot of questions that have come in live, so that's great. So from Ben, it is the unit of texture index MRD squared? That's a great question.
Yeah.
I think we're going to have to get back on that one.
Yeah, I'd have to look at the reference for that.
Yeah, so what I do know is that the smaller the number, the less texture.
Effectively, yeah.
Yep. The higher the number, the more. And it does not just stop at 1.
Right.
So we'll have to get back to you on that one, Ben. Also from Ben, can you evaluate the process symmetries in DIFFRAC.TEXTURE software? I think we talked about that a little bit, process symmetry.
Yeah, exactly. So by looking at, with the component model, you can kind of see where you're having more constraints on process symmetry versus less. Things like that. I don't know if you have anything that you
I mean, one thing I really like about the component method, because we are modeling it with discrete components, whether it's a spherical component or an elliptical component, or for that matter, the fiber component, it gives you a value of the width. So it tells you, in terms of that rotation, how much orientation there is. If it's, is it 1 degree of rotation? Is it 5 degrees? That number you can get out of that component. I think if maybe we bring one of those up, and we can see that number.
So we go to evaluation component, and you can see sort of these values.
Those are the spreads.
About, right?
Yep.
Let's see if I can drag
So, and it's right there in degrees. You have the phi 1, phi, and phi 2. That gives you that three-dimensional orientation.
And then you get the spreads.
But then the spreads there, those tell you how well aligned those are. Of course, the smaller the number, the stronger that
And if you
orientation.
do spherical modeling, it's simpler than this, right? So,
all right. Another one from Ben. Ben, thanks for sending a lot of questions here. For me, it always is challenging what symmetry to choose from. I'm hoping for an easier user software in that case. Why can't we just put the space group and move on? It's a great point. So, and this goes back to the idea of symmetries, right? Crystal symmetry versus process symmetry. Let's talk a little about that.
So crystal symmetry is going to basically be fixed depending on how the unit cell, you get different reflections in different directions. So you're going to see different things in your pole figure because of that. When we talk about process symmetry, we're more talking about constraining the symmetry in the actual pole figure itself. So like the example we showed with the orthorhombic versus monoclinic process symmetry. You can kind of see, I don't remember which one of those that was. It might have been these first two. Hang on, let me see if I can pull it up. Yeah, so that's orthorhombic versus monoclinic.
So orthorhombic, that's imposing four-field symmetry. Yeah. Obviously, when you look at the left, that left column, you can see it is different.
Right.
It is not fourfold. It is different from the top to the bottom. But then we're imposing that symmetry on it, the orthorhombic.
Exactly.
Yeah. Sometimes that's good.
Yeah.
Sometimes that's good because it does kind of force the model into a more stable state.
That's something where you can kind of do some background investigation and figure out what is going to be the most reasonable process symmetry for me, for my material system.
Right.
And you can just do it based on looking at the pole figures as well.
Yeah.
Yep. Like we did, what we did.
Yep, and I can understand that there is some confusion because we're using similar names.
Right.
Orthorhombic is a crystal symmetry. Triclinic, monoclinic, these are terms that are used in crystal symmetries too. But just in your mind, keep that difference. Crystal symmetry is about relating pole figures to each other.
Exactly.
Whereas process symmetry is the symmetry involved in the orientation of the crystallites. So that is the differential there. Now, another way, though, that the user interface does help you is with the process symmetries is you can choose certain symmetries that are common, like you had said.
Yeah.
If you're working with brass moves certain ways. It has certain slip planes. Same thing with aluminum or other materials, and that's why we have those built in. You can build your own too, but just put together some components. All right. And then, Ben, one more question here from him. Since when can we tilt the source in the D8?
That's a good question. I'm going to defer to you on that.
I believe it's in the latest version of the software. The measurement software.
For the collection of pole figures?
Yes.
Yeah, okay.
Yeah. So we implemented it when we did release the D6. And so I believe that we have released a newer version of the measurement software.
It's very common for stress measurements. We do that, like, I don't know, since like the beginning of time, I feel like, right? Yeah. Yep. So, it's something that's newer for texture, though, I believe.
Yep. So it is in there. And remember, it's not just the source. It's about biasing the source and the detector. All right. So, on to another question, one that had come in before from Cynthia. When I collect texture data on my epitaxial thin films, I often miss peaks. Any suggestions there? I remember I had a problem like this once. I was sitting there and I knew, silicon stuff, we always grow on silicon or STO, something cubic, right? For thin film growers, material scientists, it's like it's either cubic or it's pseudo-cubic, right? And we do the pole figure, and what? I only have 3 peaks.
Yeah.
What's going on here? I'm missing one of them. What? Why is Cynthia missing peaks?
Well, it's a great question. And I think it probably has to do with the step that you're taking in your pole figure collection. So probably smaller steps. If you have something that's really highly oriented, you're going to see a really, really small spot in the orientation distribution function. Yeah,
with these metals, things like that, you're talking
much softer.
Phi rotations are what? 5 degrees?
Yeah, typically like 5 or 6 degrees. I think I collected this data with 6 or 7 degrees.
Yeah, one thing that's kind of cool in a wizard, you can go back, watch that previous episode, is how you actually don't have to do a discrete step. You could tell it, I want the same resolution across the pole figure. So it'll do bigger steps at the higher tilts, smaller steps at the lower.
Right.
And 3, 5 degrees. But for a film, if you think about it, single crystal substrate, 0 broadening.
Yeah.
If you're using something like a microfocus, a Montel, divergence, axial, 0.03, 0.05.
Yeah, roughly, 0.03-ish.
So even if you use a 0.1 step, you could go nothing to nothing.
Right, exactly. Doing a continuous rotation will help with that.
That is also a great suggestion. So continuous rotation, just keep in mind the resolution then is going to be dependent on the step size ultimately.
Exactly.
Sometimes it's going to take a while to collect it because of the step size.
Right.
Yeah. Also, 2D detectors I always found great for this type of
It
stuff.
is super helpful because then you're just getting you're getting so much information in one frame.
Yeah, yeah. But it is nice for epi stuff if you want to see what's that relation substrate to the film. Man, you get the two pole figures right next to each other.
Yeah.
Really great. All right, next question from James. How many different tilt angles are required for high fidelity pole figure analysis? That's a great question, James. So how many different tilt angles do we need?
So kind of like the incremental steps that we took, the 5-degree steps in rotation. I think I did, depending on my 2D coverage, I kind of have the advantage of the 2D detector, right? So typically my coverage in psi tilt is pretty good with the 2D detector. I think I did 5-degree steps with the D6 in tilt up to the Bragg limit in the case of the D6. I try to go up to 60 degrees with when I'm doing multiple pole figures in the D8, for example.
Yeah.
Just so you have enough coverage there to be safe. I think theoretically you could get away with less if you collect more pole figures.
Yeah, and I would say it's also, unfortunately, it's one of those things, it depends on your sample.
Right, it always does.
If you're talking about really strong texture, talking about tiny spots, you're going to have to bite the bullet, do smaller steps. But 2D, game changer here.
Yeah, that's where it really helps you.
Game changer, because now in psi, in the tilt direction,
you basically have continuous coverage.
It's continuous. Just make sure that you got a little bit of overlap. You're good to go. You do have to think about phi.
Yeah.
So like you said too, maybe start with 5 degrees or so, 3 degrees, and then balance what's important to you.
Exactly.
So speaking of, actually, this might be a question, but
I know exactly what you're going to say.
How long?
The
How long does this stuff take?
Right.
Yeah.
So for both instruments, this data collection was roughly an hour to 2 hours.
Really?
For all
Even
the
for the
figures.
D6?
Yeah. 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 I mean, we're using slit optics with the D6, but the measurement circle is so small. One of the nice things about the D6, if you opt for the motorized slit, you can do fixed sample illumination and get even more intensity.
Okay.
So there are some really nice things about the D6. It's still a little bit slower than the D8. That's expected, though. I mean, you're paying a lot more for that instrument.
Yeah, I mean, you collected the data specifically to have the same time, same conditions. If you really wanted to on the D8, you probably could have taken this in like 5-10 minutes.
For sure, yeah.
For the whole thing. All right. Next question from Fabian. You choose positivity reinforcement. How comes that? Why do you have negative values on your pole figures? Because you chose positivity. What's going on here?
Great question. So it only minimizes the negative values. It doesn't zero them out completely, from what I've seen. It does help in terms of eliminating a lot of that noise in the ODF, though.
Yep. And there are 2 steps in that. There is the first step for spherical harmonics is the actual fit, and that's where you choose the index on the top.
Yep. And then the augmented rank.
Now the augment on the bottom, that's how it reconstructs things.
Yep.
And so when you choose a higher index down there, well, now you can get those sharper features, which can turn and pop out a negative value.
Exactly.
All right. So, question from Wanuk. The 2D image does not contain full azimuthal diffraction. In this case, how does the pole figure can tell all orientations of a specific HKL? Because the material is highly symmetric aluminum. So I think the idea is you're not getting pole figure coverage. You're not getting whole pole figure coverage. So how is it that you can reconstruct it here?
So yeah, with the 2D snapshots, we are only seeing a portion of the Debye ring, right?
Yep.
So we make up for that by basically rotating and tilting the sample at different steps.
Yeah, so in your data collection, there's actually 2 psi tilts, right?
Yeah. Yes, yeah.
Yeah, and when you go into the wizard, it'll actually show you. It's kind of nice, right? It takes into account the geometry, the shadowing, everything, and you can see. It'll show you the little arc of coverage.
And that's from the 2D detector.
From the 2D detector, and then you put another arc in, and you can see and make sure it's a little bit of overlap.
Yeah, and we went over that in the last video.
Yeah, so if you watch that last video, you see that. So that's in psi.
Yeah.
Now in phi, how does it fill it in? It interpolates it.
Yeah, pretty much.
It interpolates it. Yeah. And the other, like I said before, the cool thing is that in the software you can actually choose consistent resolution.
Right.
So what it'll do is, as you know, in the middle of the pole figure where you have a high density, it'll take less 5s, and then on the outside it'll take more 5s.
Right. With the 0D, I actually do the, what do they call it, non-thinned mode?
Yeah.
Yeah, just because I'm going to be rotating at the same speed usually.
Yeah. So that's how we handle that, interpolation. Next, from James, is there a 3D visualization method for the ODF?
There is, as a matter of fact, in the software, yeah.
And I will say this, let's do it.
Yeah, okay. Let's take
Spherical harmonics doesn't work as well because it's got so much noise in the background. But when you do the component method, yeah, it actually looks pretty
So one
nice.
thing that, before we go into that, I'll just show, you can look at the different
cuts.
Basically cuts in the different directions, so that's pretty cool. And then we can go ahead and construct ODF 3D view, and you can see what that looks like in 3D.
Yep. So there we go. So this works really well for component. Like, go to the spherical harmonics one and do it.
Yeah, let's see. Harmonic. That looks pretty good.
My technical people always get upset when I do things like this. I'm like, just show it, just show it.
Yeah, no.
But it'll look bad.
It's there.
That's okay, just do it.
All right, ready? So we go to the ODF for the spherical harmonics. You go to View, ODF 3D view, and
so you can see it's got a lot more of that noise in there.
Exactly.
And that's because that circle harmonic method is trying to fit everything. So it's throwing it all in there. So a little bit harder to see. But if we, you know, the other one, so click on the good one.
So if I go back.
If you go back to the component method, just much cleaner in terms of really representing what's going on there.
Yeah.
In terms of the 3D space. All right, from Wanuk. Question number 2, is the data that was measured PXRD using a 2D detector, is it better if one can use SCXRD machine for measuring pole figures, and what is the benefit? So starting with the question about the data, how was it collected? What kind of detectors did we use?
So these are on the floor standing model. It's a 2D Eiger detector. On the benchtop, it's a 0D, 1D Lynx IXET. I collected that in 0D mode. So basically, phi scans, and then tilting, and then phi scan, tilting, yeah, like that.
Okay, so that's how we did it there. Now the second part of that, is it better if one can use an SCXRD machine for measuring the pole figure? So most single crystal machines are equipped with a 2D detector, something like, say, a photon detector. They do typically have point sources. I do believe they are capable of some scheming for this. It is, I think the Wizard is a little bit more advanced in calculating your overlaps and things like that for the powder machines. What would the benefit of an SCXRD machine? I think the biggest benefit, if you have it.
Yeah.
You know, use the machine you have access to.
Can you put big samples on there, though? I mean,
yeah, I mean, typically a little bit more limited to smaller things.
Yeah. And so then the issue of crystallite sampling could be a problem.
Yeah, I mean, one benefit too would be you can get on the single crystal machines, because they are kind of constructed a little differently. You can get the detector real close.
Oh yeah, you get a lot of
coverage.
Yeah, for sure.
So with the benefit though of the powder machine, because we use the detector like an Eiger, it has better energy discrimination. You get any fluorescence going on there, that's going to take down the background. So, I mean, 2D has been around, though, I would say, in what we call a powder machine for a very long time, going back to the high star detectors. So 20, 30 years we've been doing
before
this.
my time.
Yeah. All right, from Fabian. Hi, James. For 0D or 1D detector, the step in tilt is usually 10 or 5 degrees, according to the accuracy you want. With a 2D detector, you need much less. Gamma range gives you the range and the tilt. So I think just clarifying. Okay, from Gokay. What if we add dozens of random components? Will we get a good refinement?
I am thinking of what my colleague Nathan Henderson tells me, is you can get as good of a fit as you want, with the least amount of constraints. But do you get a real answer?
Yeah.
That's the question.
And actually, one of the origins of the component method, if you go back to some of the original literature that was published by Kurt, it was that he actually would insert thousands of components, thousands of spherical components in every possible orientation. And then he would send that over to a supercomputer and do that refinement. And in that way, yeah, you can fit it out.
Yeah.
Because you're basically modeling every point in the ODF space. And it does work.
Yeah.
It just requires a lot of computing power. And in the end, you do question, do you have the stability of things like fiber, putting in a fiber component, putting in an elliptical component, things like that.
Exactly.
So the answer is yes. I mean, go ahead. You can add them. Be cognizant that you can fit anything with enough random variables.
Right.
And also, in the end, what are you looking for here?
That's really what it comes down to. I mean, I love simple answers.
Yeah.
Right. And so
simple is often more right.
Yeah.
So from Ben, is the update of the software free of charge so we can get ellipse components and get rid of some existing bugs?
I think the 4.1 to 4.2 would be included, right? That's for a free of charge upgrade?
Yeah, I believe if we're still within the same version number, then you're good to go. Yeah. But a good, if you have a question specifically on that, you can always send it into our service group, and they can get you a specific answer for your scenario. But ultimately, you could also just go to brukersupport.com, download it, try it out, see what it says. From James, okay, more components will always improve your fit, but penalize the statistical significance interpretability. There we go.
Yeah.
Another question that had come in before, from Ryan, how should the sample be mounted relative to the process direction? We talked about that a little bit.
Yep, we did. Great question. So the generic way is sample, or I guess the source to detector is the rolling direction in the picture, right? And then transverse is going to be in and out of the goniometer. And then normal is straight up. Yeah. So the sample should be mounted if you're a metal person in the rolling direction. The direction that you rolled it in should be pointing towards the detector.
And if you're doing a lot of samples, make a mark on them.
Yeah, that
helps.
Give
some consistency. Maybe along a certain edge. Always mount it. So
and that's what I did not do with this. But you can still play around with the software and rotate it if you need to.
Yeah.
So it's nice.
All right. So from Wanuk, why inverse pole figure is required? What is the benefit compared to regular pole figure?
It's just a different way to look at it. Yeah. So a lot of, I guess, in metallurgical applications, they want to see what the textures are in the lab frame, basically. Yeah. So what crystallites or directions are pointing in what directions in the lab frame?
Yeah. I mean, so a pole figure, what you're representing is a single HKL in the lab's coordinate sphere. On the other hand, in an inverse, you're picking a certain lab sphere direction, and then you're showing all of the different HKLs present in that direction.
Exactly.
So, and that's why they call it inverse. Like you said, metallurgists, the go-to.
Yeah.
Part of this is that idea that texture analysis has kind of grown up out of different areas. So, geologists, they love pole figures.
Yeah.
Some physicists love pole figures. Metallurgists, like you said, they just want to see your process directions.
Yeah.
All right. And then we had one more question that came in from Taylor. How many pole figures are needed to generate an ODF?
So, I would say 3 of reasonable coverage on the pole figure. If you have less than like a certain degree of coverage, maybe like less than 50 degrees, maybe you want a little bit more.
Yeah.
More redundancy. But I've gone down to 2, and I've gotten the same results with enough coverage.
Yeah, if you have high process symmetry, high crystal symmetry,
for cubic,
less required. Me, I've always at least said 3.
Yeah, that's always
feel better with 4.
Yeah.
They were pretty good there. We start getting like 6, 8.
Yeah.
Kind of more than what you need.
The diminishing returns. Yeah. Exactly. Yeah. I agree. I think the gold standard is 4.
All right.
3 to 4.
All right, and with that, we have come to the end of our time. So thank you, everybody out there, for joining us today, staying a little bit later. Hopefully we answered all of your questions and got all that information. Thank you, Jonathan, for joining us again.
Thank you for having me. Always a pleasure to be here.
Yeah, always very informative to learn about these kind of advanced topics and this deep dive, especially with the data that you brought.
Yeah, of course.
Really, really informative. So thanks for bringing that in. So until next time, though, make sure that you keep your signal high and your background low.